Hi everyone, welcome back. If you are here tonight, then you have found a quiet place to rest. And that is a very good thing. There is nowhere else you need to be right now. There is nothing else you need to do. You can simply settle in, close your eyes whenever feels right, and let the words wash over you like a soft, steady tide. Tonight, we're going to talk about something very old, and very peaceful, and very beautiful. We're going to talk about our sun, about its long, slow life, about the quiet, gradual way that all stars, even the ones that give us warmth and light, eventually come to rest. And we can take a moment to notice that this is not a sad story. It is a very long, very gentle story. A story of transformation, of matter becoming something new, of light that has traveled for billions of years. Slowly, softly, finding its way to you. The sun has been burning for about 4.5 billion years, and it will continue burning for roughly another 5 billion years after tonight. So there is truly no rush here. There is no urgency. We have all the time in the universe. So let your breathing slow down a little. Let your body feel heavy and warm. And let's take this journey together, slowly, gently, through the long and quiet life of the sun. Our sun, the one we feel on our skin each morning, is what scientists call a yellow dwarf star. It sits comfortably in the middle of its life, burning hydrogen deep in its core. And this process, called nuclear fusion, is remarkably calm and steady when you think about it from a cosmic perspective. The sun has been doing the same thing, fusing hydrogen atoms together into helium every single second for 4.5 billion years. That is about 4.5 billion years of slow, steady, patient burning. And we can take a moment to notice how comforting that constancy is. The same sun that warmed the first oceans on Earth is warming us now. The same light, the same gentle nuclear fire. Slowly, gently, day after day after day. Without interruption, without complaint, without end, at least not for a very long time yet. The sun is, in terms of pure size, almost incomprehensibly large compared to our everyday experience. If you hollowed out the sun and tried to fill it with copies of the Earth, you could fit approximately 1.3 million Earths inside it. And yet, compared to many other stars in our galaxy, the sun is actually quite modest in size. There are stars out there so large that if you place them where the sun is, they would swallow up not just Earth, but Mars, and Jupiter, and even Saturn's orbit. And we can take a moment to notice that size, in space, is relative. The sun feels enormous to us because we live near it. But in the grand, quiet landscape of the Milky Way, it is one ordinary, medium-sized, peacefully burning star among roughly 200 billion others. There is no need to rush through that thought. Just let it settle gently. Right now, at this very moment, the sun is converting about 600 million tons of hydrogen into helium every single second. That sounds like a very large number, and it is, but the sun is so vast, so deeply full of fuel, that this conversion barely makes a dent in its total reserves. The sun has been doing this for 4.5 billion years, and it has used up only about half of the hydrogen in its core. Half. It is, in the most literal sense, only halfway through its main life, like a traveler who has walked half a journey and still has the whole second half ahead. Slowly, gently, the sun continues its work, and we can take a quiet moment to think about what it means to have that kind of deep, patient energy, to burn steadily and warmly for billions of years without rushing, without exhausting yourself, without hurrying. The surface of the sun, the part we would see if we could look directly at it, is called the photosphere. It glows at a temperature of approximately 5,500 degrees Celsius. That is very hot by any human measure, but it is actually much cooler than the sun's core, which burns at around 15 million degrees Celsius. And strangely, the outermost layer of the sun's atmosphere, a wispy, beautiful region called the corona, is even hotter than the surface, reaching temperatures of 1 to 3 million degrees. Scientists are still working to fully understand why this happens. It is one of the quiet mysteries that the sun keeps to itself. And we can take a moment to notice that even something as familiar as the sun still holds gentle secrets, still has quiet things to teach us, still offers new questions to wonder about on a soft, unhurried evening like this one. Light from the sun takes approximately 8 minutes and 20 seconds to travel from the sun's surface to the earth. This is a thought that feels very soft and dreamy when you sit with it. The sunlight that warmed your face this afternoon left the sun 8 minutes earlier. It crossed 150 million kilometers of empty, quiet space in that time, and before it even reached the surface of the sun, that light spent an extraordinary amount of time traveling through the body of the sun itself. A single photon of light produced in the sun's core can take anywhere from 10,000 to 170,000 years to slowly, gradually work its way from the core to the surface, bumping and scattering through the incredibly dense solar interior. Slowly, gently, it makes its way outward. Then it crosses space in just 8 minutes. There is something deeply peaceful about that long, patient journey. The sun rotates on its axis, just like the Earth does, but in a very different way, because the sun is made of gas, a giant, dense sphere of plasma. Different parts of it rotate at different speeds. This is called differential rotation. Near the sun's equator, one rotation takes about 25 days, but near the poles, a single rotation takes closer to 35 days. So the sun is not spinning as one solid body, but rather flowing and turning in layers at different rates, like a very slow, very enormous whirlpool. And we can take a quiet moment to imagine that. The vast, warm, golden disk of the sun, turning slowly, different layers gliding past each other in a gentle, unhurried rotation. There is something almost meditative about it. The sun, like us, is not perfectly uniform. It has its own rhythm, its own soft, complex motion. The sun has weather, not weather like rain or snow, but its own kind of dynamic, shifting surface activity. There are sunspots, which are slightly cooler, darker patches on the sun's surface caused by intense magnetic fields. These sunspots come and go in cycles that last approximately 11 years. At the peak of this cycle, called solar maximum, the sun's surface is alive with activity. At the quiet end of the cycle, called solar minimum, the surface is much calmer and smoother. And we can take a moment to notice that even the sun has quiet seasons. Even the sun has times of rest and times of gentle activity. Right now, as you settle in for sleep tonight, the sun is somewhere in one of its 11-year cycles, slowly, gently, progressing through its own rhythm, its own pattern, its own long, peaceful routine. The color of the sun, when seen from space without the filtering effect of Earth's atmosphere, is actually very close to white. Pure, clean, white light. It is our atmosphere that scatters the blue wavelengths of sunlight and makes the sun appear yellow or golden in our sky, and deep orange and red near the horizon where the light travels through more atmosphere. So the golden sun we know and love is partly a gift of our own air, our own blue sky, bending and softening the light before it reaches our eyes. And we can take a moment to appreciate that beautiful collaboration, the sun sending out white light, and the Earth's atmosphere receiving it and gently painting it gold. Slowly, gently, light becomes color, and the familiar warm sun of a summer afternoon is, in a lovely way, a portrait painted by our own planet's air. Deep inside the sun, in the very core, the pressure is so extreme that hydrogen atoms are squeezed together until their nuclei fuse. This fusion releases energy in the form of gamma rays, very high-energy light. But as we mentioned softly a moment ago, this light does not travel directly outward. It bounces and scatters through the dense interior for thousands of years, slowly losing energy at each interaction, gradually transforming from gamma rays into lower energy forms of light. By the time that energy emerges at the surface, it has been downgraded from fierce gamma radiation into the gentle visible light and infrared warmth that we feel on our skin. And we can take a quiet moment to think about that transformation. Something that began as an intense burst of energy, slowly, gently, over thousands of years, becomes the soft warmth of a morning sunbeam. There is something very tender about that long, slow softening. The sun produces something called solar wind, which is a constant, gentle stream of charged particles that flows outward in all directions from the sun's upper atmosphere. This solar wind travels across the entire solar system, all the way past Pluto and beyond, filling the space around our star with a thin, invisible, flowing stream of particles. When this solar wind reaches Earth, our planet's magnetic field gently deflects most of it. But near the poles, some of the particles slip inside the magnetic field and spiral down into the upper atmosphere, where they collide with air molecules and create the aurora borealis in the north and the aurora australis in the south. Those soft, glowing curtains of green and pink and blue light that dance in the polar skies are, in a very real way, the sun's breath, gently touching our atmosphere and leaving a quiet trail of light. There is no need to rush. Just let that image settle softly, gently moving forward. The sun, as we have been noticing, is currently in the longest, most stable phase of its life. This phase is called the main sequence. All stars spend the majority of their lives on the main sequence, fusing hydrogen in their cores in a steady, balanced way. The sun entered the main sequence about 4.5 billion years ago, and it will remain there for roughly another 5 billion years. That is 10 billion years total on the main sequence. 10 billion years of steady, calm, continuous fusion. And we can take a moment to notice how that kind of deep, slow stability is in itself a form of beauty. Not dramatic, not sudden, just patient, quiet, consistent work, continued over a span of time so large that it gently dissolves any sense of urgency. Slowly, gently, the sun does its work, and for now, it will continue. The sun is about 4.6 billion years old. To put that in a very soft perspective, the Earth is about 4.5 billion years old, meaning Earth formed quite soon after the sun did, from the leftover gas and dust of the same enormous nebula that became the sun. They are, in a way, siblings. They formed together from the same quiet cloud of material. And the sun has been the Earth's companion for essentially all of Earth's existence. Every living thing that has ever existed on this planet, every tree, every ocean creature, every quiet insect in the grass, has existed under the light of this same Sunday, the same patient star that is shining right now, over the darkened half of Earth where you are resting, has watched over all life on this planet for billions of years. Slowly, gently, always there. Now, as we continue, scientists can measure how old a star is, and how far through its life it has come, by studying its composition and its light. When they analyze the light from a star, they can see the fingerprints of different elements in the spectrum, dark lines at specific wavelengths that reveal which atoms are present. From the sun's spectrum, scientists can tell exactly what the sun is made of: about 73% hydrogen, about 25% helium, and roughly 2% of everything else: carbon, oxygen, iron, calcium, and many other elements. And we can take a moment to notice that the sun is mostly hydrogen, and that as the years pass, it is slowly, steadily converting that hydrogen into helium. Over billions of years, the ratio changes. The sun's composition is its autobiography, written in light, slowly unfolding over time. One of the quieter, gentler aspects of the sun's physics is the concept of hydrostatic equilibrium. This is the balance that keeps the sun the size that it is. On one hand, gravity is constantly pulling all of the sun's mass inward toward the center. On the other hand, the immense pressure and heat produced by nuclear fusion pushes outward. These two forces, gravity pulling in, fusion pushing out, are perfectly balanced. The sun sits in a state of exquisite, continuous equilibrium, not growing, not shrinking, just holding steady. And we can take a moment to appreciate that balance. The sun is not exploding outward, and it is not collapsing inward. It is simply balanced, in a state of soft, dynamic stillness, maintained every second of every day for billions of years. There is something almost restful about that image. Let's take a quiet moment to think about the neutrinos that the sun produces. In addition to light and heat, nuclear fusion in the sun's core releases enormous numbers of tiny, nearly massless particles called neutrinos. These neutrinos are so small and so weakly interacting that they pass through the entire body of the sun in just 2 seconds. And they pass through you and the Earth just as easily. Right now, as you lie quietly, about 65 billion neutrinos from the sun are passing through every single square centimeter of your body every second. Through your hands, through your closed eyes, through the pillow beneath your head. They pass through the Earth as if it were not there at all, and continue their journey into the cosmos. You are, in a very real sense, bathed in the sun's ghost light even in the deepest darkness of night. The sun's gravity holds the entire solar system together. Everything that orbits the sun, the 8 planets, the dwarf planets, the asteroids, the comets, the countless icy bodies in the outer solar system, they all stay in their orbits because of the sun's gravitational pull. And the reach of this gravity extends very far. The outermost edge of the sun's gravitational influence, a region called the Oort cloud, may extend as far as 1 to 2 light years from the sun. 1 to 2 light years. That is an enormous sphere of gentle gravitational influence, filled with ancient icy objects that have been in their quiet orbits since the solar system formed. And all of them, slowly and silently, in their own way, are held close by the same patient star that has been burning for 4.5 billion years. Slowly, gently, together, the sun, for all its quiet steadiness, does occasionally release large bursts of energy. These are called solar flares and coronal mass ejections. A coronal mass ejection is when the sun releases a large cloud of magnetized plasma into space. When a large one is directed toward Earth, it can disturb our magnetic field and cause geomagnetic storms. These storms are, for the most part, quite harmless to life on Earth's surface, but they can cause beautiful auroras to be visible much further from the poles than usual. Gently moving forward, these events are simply part of the sun's natural breathing, its own quiet fluctuations, its 11-year rhythm of activity and rest. They are not catastrophes. They are the sun, in its long and patient life, shifting and adjusting, the way any living system gently moves and changes over time. There is a region just below the sun's visible surface called the convection zone. In this region, hot plasma rises from below, releases its heat near the surface, cools slightly, and then sinks back down, and then rises again. In a slow, continuous cycle, this process is called convection, and it is the same process that moves warm water in a pot on a stove. On the sun, these convection cells are enormous. Some of them, called granules, are about the size of the state of Texas, and they cover the entire surface of the sun in a slowly shifting, quietly bubbling pattern, constantly rising and falling, rising and falling. If you could watch the surface of the sun in extreme slow motion, it would look like the surface of very slowly simmering, very bright golden soup. Slowly, gently, always in motion. The sun's core is the only region where nuclear fusion actively takes place. The core extends from the center to about 25% of the sun's total radius. In this region, the temperature is 15 million degrees and the density is about 150 times that of liquid water. Under these extreme conditions, hydrogen nuclei, which are just individual protons, are fused together to form helium nuclei in a process called the proton-proton chain. This chain has several small steps, and in each step, tiny amounts of mass are converted directly into energy, following Einstein's famous equation. And we can take a moment to notice that everything, the warmth on your face, the light in the sky, the slow drifting of summer clouds, all of it originates in these quiet nuclear reactions, deep inside the sun, where protons gently merge, millions of times per second, at temperatures we can barely imagine. Now, as we continue, the sun does not burn in the way that a fire burns. Fire is a chemical reaction. It requires oxygen and fuel. The sun needs no oxygen. It is a nuclear reaction, happening under conditions so extreme that the ordinary rules of chemistry don't apply. The sun could not burn in the chemical sense even if it wanted to. This is why the sun has lasted for billions of years, rather than burning out in a few thousand years. As scientists in the 19th century once worried, before nuclear physics was understood, there was genuine scientific debate about how the sun could have been shining for long enough to explain the geological and biological history of the Earth. The answer, when it finally came with the discovery of nuclear fusion, was both beautiful and deeply calming. The sun is not burning. It is slowly, patiently, merging atoms together, and it has enough fuel to do so for another 5 billion years. Gently moving forward, in about 5 billion years from now, the sun will begin to change. The hydrogen in its core will gradually run out. Over millions of years, slowly, gently, the core will start to shrink as fusion begins to slow. But this is not the end. It is more like the beginning of a long, quiet transition. The sun will not simply switch off. It will transform, slowly and majestically, into something quite different and, in its own way, quite beautiful. And we can take a moment to notice that this transformation is not rushed. It unfolds over timescales so enormous that they are almost impossible to feel as urgent. By the time the sun begins to change in this way, our entire recorded human history will have repeated itself millions of times over. There is truly no need to worry. The sun has a long, full life still ahead. As the hydrogen in the sun's core runs low, the fusion will shift outward into a shell surrounding the increasingly inert helium core. This shell of hydrogen fusion will actually produce more energy than the core fusion does now. And this extra energy will cause the outer layers of the sun to expand. Very slowly, over many millions of years, the sun will begin to swell. It will grow larger. It will cool slightly on its surface as the energy spreads over a larger area. And as it cools, it will shift in color from its current yellow-white to a deeper orange, and then to a rich, warm red. This is the beginning of what astronomers call the red giant phase. The sun, in its old age, will become a red giant, a vast, warm, gently glowing sphere much larger than it is today. Slowly, gently, it will fill more and more of the inner solar system. Let's take a quiet moment to think about how familiar this process is elsewhere in nature. Many things in the universe go through phases. They begin, they grow, they peak, they transform, and they rest. Stars do this too. The sun's life follows a recognizable arc that it shares with billions of other stars across the galaxy. The red giant phase is not unique to our sun. It is a natural, common, well-understood phase of stellar aging, and we can find comfort in that commonness. The sun is not doing anything unusual. It is simply living its life, the way stars live their lives, in the same patient, unhurried way that stars have always done. All across the universe, stars are moving through these same phases right now, quietly, slowly, following the same gentle arc that our sun will eventually follow. During the red giant phase, the sun's outer layers will expand dramatically. Current models suggest that the sun may eventually expand to roughly 200 times its current radius, and possibly more. To give you a very soft sense of this, the sun currently has a radius of about 696,000 kilometers. 200 times that is about 139 million kilometers. The Earth is currently about 150 million kilometers from the sun. So in the red giant phase, the sun may expand to fill almost all of the space currently between it and the Earth. And we can take a moment to notice that by this time, life on Earth as we know it will have long since changed beyond recognition, or perhaps moved on entirely, due to the slowly increasing brightness of the sun over the intervening billions of years. These changes are gradual. They are measured in millions and billions of years. Slowly, gently, always slowly, as the sun begins to swell into a red giant, something interesting will happen to the planets. The innermost planet, Mercury, will almost certainly be engulfed by the expanding sun and will cease to exist as a separate body. Venus, the second planet, will very likely face the same fate. Earth's fate is less certain and depends on the precise details of how the sun expands and how much mass it sheds during the process. Some models suggest Earth will be engulfed. Others suggest it may survive, though in a completely unrecognizable form. And we can take a moment to notice that these are not events to be feared tonight. In this warm, quiet moment, they are very distant futures, gentle, slow-motion transformations unfolding over billions of years. They are simply part of the long story that the universe tells itself. Very slowly, in the deep quiet of time, gently moving forward. One reason astronomers study red giants with such careful interest is that we can see many of them across our galaxy right now. They are bright, relatively cool stars that glow with a deep reddish-orange light. Some of the most famous stars in the night sky are red giants. Arcturus, one of the brightest stars visible from Earth, is a red giant about 25 times the size of the sun. Aldebaran, the red eye of the Taurus constellation, is a red giant about 44 times the size of the sun. When you look at these stars on a clear night, you are seeing a preview, a very distant, indirect preview of what our own sun will one day look like. You are seeing stars that have already traveled the road that our sun is still walking toward. Slowly, patiently, over billions of years to come. There is a concept in astronomy called the habitable zone, the region around a star where liquid water can exist on the surface of a planet. Right now, Earth sits comfortably within the Sun's habitable zone. But as the Sun gradually brightens over the next billion years or so, the habitable zone will slowly drift outward. What is currently warm enough for liquid water on Earth may eventually become too warm. And as the Sun expands further into a red giant, the habitable zone will move far out, perhaps to where the asteroid belt is now, or even further toward Jupiter. Slowly, gently, the conditions for liquid water will shift across the solar system. Some of the currently frozen moons of Jupiter and Saturn might even briefly thaw. And we can take a soft moment to imagine that, in the far future, perhaps quiet oceans on distant moons, briefly, gently warmed by a swelling red giant that was once our familiar golden Sunday. Now, as we continue quietly, the red giant phase of the Sun will not last as long as the main sequence. While the main sequence lasts about 10 billion years, the red giant phase is expected to last only a few 100 million years. In cosmic terms, it is a relatively brief transition, though still far beyond any human timescale. During this time, the Sun will be visibly different from what it is today. It will be larger, redder, cooler on its surface, and much brighter in total output. The night sky, or what would be the night sky for any observer in the outer solar system, would look quite different. The Sun would be a vast, warm, glowing red disk, much larger than it appears to us now. And we can take a moment to imagine that sky, deep and dark, filled with stars, with a great warm red glow occupying a large portion of the inner solar system. Softly, quietly, beautiful in its own ancient way. Let's take a quiet moment to think about what is happening inside the Sun during the red giant phase. While the outer layers expand and cool, something very different is happening at the center. The helium core, the ash left behind from billions of years of hydrogen fusion, is slowly contracting under gravity. As it contracts, it heats up, slowly, gently. The temperature in the core climbs higher and higher, until it reaches approximately 100 million degrees Celsius. At that point, something new begins. A new kind of nuclear fusion ignites, helium fusion. 3 helium nuclei fuse together to form a carbon nucleus. This is called the triple alpha process. And this moment, the ignition of helium fusion in the core, is called the helium flash. It happens quickly in cosmic terms, but it is not a destructive event. It is more like the Sun taking a deep breath and beginning a new chapter. The helium flash is one of the more dramatic events in the quiet life of a star, but it is not visible from the outside. All that energy is absorbed within the Sun itself. After the helium flash, the Sun settles into a new, quieter phase of helium burning in its core, and its outer layers actually contract slightly back in from the enormous red giant size. The Sun will spend roughly 100 million years fusing helium in its core in this new, more compact configuration, and we can take a moment to notice how even in its later life, the Sun finds a new balance, a new equilibrium, a new steady state, just as it balanced gravity and fusion pressure during the main sequence. It finds another balance during the helium burning phase. The universe seems to have a quiet preference for balance, for steady states, for things that gently settle rather than simply ending, gently moving forward. After the helium in the Sun's core is exhausted, the Sun will once again expand. The outer layers will swell outward again, even further than before. And now, something gentle and beautiful will begin to happen. The outer layers of the Sun, the thin, wispy, extended atmosphere, will begin to drift away into space. Slowly, over thousands of years, the sun will shed its outer envelope. This is not an explosion. It is a slow, quiet release. The outer layers will drift outward in a roughly spherical shape, expanding slowly into the surrounding space, thinning as they go, forming what astronomers call a planetary nebula. The name is a bit misleading. It has nothing to do with planets, but it is one of the most visually beautiful phenomena in the known universe. A soft, glowing cloud of gas, gently expanding into the darkness. Planetary nebulae are, in many ways, among the most visually beautiful objects in the night sky. They glow in soft colors, blues, greens, pinks, reds, because the gas is being illuminated and energized by the exposed core of the dying star at their center. Some of the most famous ones have names that reflect their shapes. The Helix Nebula, sometimes called the Eye of God. The Ring Nebula, a soft glowing ring in the constellation Lyra. The Cat's Eye Nebula, a complex, layered structure of expelled gas. Each one of these was once a star like our sun. Each one represents a star quietly releasing its outer layers, sending them gently back into the galaxy, recycling itself into the cosmos. And we can take a moment to notice that this is not an ending. It is a transformation, a giving back, a slow, peaceful dispersal into the larger whole. The gas that makes up a planetary nebula is not lost. It joins the interstellar medium, the thin, diffuse gas and dust that fills the space between the stars. Over millions of years, this gas may eventually gather with other clouds of gas and dust to form new stars, new solar systems, new planets. The atoms that were once part of the sun's outer layers may one day be part of a new star, or a new world, orbiting a different sun in a different part of the galaxy. And we can take a soft moment to appreciate that cycle. Nothing is truly lost. Matter is simply transformed, recirculated, reused. The universe is patient and efficient in this way. It takes the old and slowly, gently remakes it into the new. Slowly, gently, over millions of years, old stars become new ones. Now, as we continue, the light that a planetary nebula produces is not continuous light like sunlight. It is emission light. Light produced when electrons in the gas atoms drop from higher energy states to lower ones, releasing photons of very specific colors. Different elements emit different colors. Hydrogen glows red and blue. Oxygen glows green and blue. Nitrogen glows red. This is why planetary nebulae can be so colorful in photographs. When astronomers photograph them, they often use filters that isolate these specific wavelengths, producing images of extraordinary delicacy and detail, soft clouds of glowing gas. Each color a fingerprint of a particular element. Each element a record of the nuclear history of the star that produced it. And we can take a moment to notice that the colors of a dying star are a kind of autobiography, written in light, slowly expanding into the night. Let's take a quiet moment to think about what the solar system will look like during the planetary nebula phase. The inner planets, Mercury, Venus, and perhaps Earth, may already be gone, consumed by the red giant. The outer planets, Jupiter, Saturn, Uranus, Neptune, will still be there, though their surfaces and atmospheres will have been altered by the intense radiation and heat of the red giant phase. As the planetary nebula expands outward, it will gently envelop these planets, surrounding them in a warm glow of ionized gas. And then, slowly, over thousands of years, the nebula will continue to expand and thin, moving outward past the planets, past the Kuiper belt, past the Oort cloud, into the interstellar void. and the outer solar system will be left quiet, dark, and cold, with only the faint remnant of the sun, a white dwarf, glowing softly at the center. Gently moving forward, planetary nebulae typically expand at speeds of about 20 to 30 kilometers per second. That sounds fast, but in the scale of interstellar distances, it means they take thousands of years to reach even nearby interstellar space. The planetary nebula that the sun produces will slowly, over thousands of years, grow from a small bright shell around the dying sun to a vast, glowing cloud light years across. By the time it has fully expanded and thinned to invisibility, it will have been traveling for perhaps 20,000 to 30,000 years. Slowly, softly, dispersing into the quiet space between the stars. And we can take a moment to appreciate the scale of that journey, a cloud of gas, born from a dying star, slowly crossing thousands of years of space to eventually dissolve into the great quiet of the interstellar medium. Slowly, gently, always slowly, the elements inside a planetary nebula are remarkable. When the sun formed, for 0.6 billion years ago, it was made mostly of hydrogen and helium, with trace amounts of heavier elements inherited from older stars that had already lived and died before the sun was born. During its long life, the sun will create new elements through nuclear fusion, helium from hydrogen, and carbon and oxygen from helium. When the sun sheds its outer layers in the planetary nebula, it will send these newly made elements, carbon and oxygen in particular, back into the interstellar medium. The carbon atoms that will make up the planetary nebula of the future sun may one day be part of organic molecules, part of the chemistry of life on some distant world. And we can take a moment to notice that the sun, in dying, will give a gift to the future universe, a contribution to the slow, patient building of complexity across cosmic time. Now, as we continue, one of the interesting facts about planetary nebulae is that they are not perfectly spherical. Many of them show complex, asymmetrical shapes, rings, jets, bipolar lobes, hourglass shapes. The reasons for these shapes are still being studied, but they likely involve magnetic fields, the rotation of the star, and in some cases the influence of a companion star if the dying star is part of a binary system. The Sun, which is a single star with no stellar companion, will likely produce a roughly spherical nebula, though with some complexity from its magnetic field and rotation. Each planetary nebula is unique, a one-of-a-kind pattern shaped by the particular history and physics of the star that produced it. Like a fingerprint, or like a snowflake, each one is different. Each one tells a slightly different version of the same quiet story. There are thousands of planetary nebulae visible in our galaxy, and astronomers have cataloged many hundreds of them in detail. They range in size from tiny, compact shells to vast, extended clouds. Some are only a few light years across. Others stretch across tens of light years of space. The Helix Nebula, one of the closest planetary nebulae to Earth at about 650 light years away, is about 2.5 light years across. If it were where the Sun is, it would extend far past the nearest stars. And we can take a quiet moment to imagine that scattered across our galaxy, right now, are thousands of these soft glowing clouds, each one the quiet aftermath of a star that once shone, that once warmed whatever worlds orbited it, that once had its own solar system, and that has now gently given its outer layers back to the cosmos. Slowly, gently, in quiet beauty, let's take a quiet moment to think about the timescale of a planetary nebula. A planetary nebula is not permanent. Over time, about 10,000 to 30,000 years, it disperses into the interstellar medium and becomes too diffuse to see. In the lifetime of the universe, which is about 13.8 billion years old, a planetary nebula is like a brief, soft flash of light. A star lives for billions of years, and then its outer layers glow for 10,000 or 20,000 years. And then the glow fades, and what is left behind, slowly, gently, is the quiet, dense remnant of the star's core. This is the white dwarf, the final, long, patient chapter in the life of a star like our sun. And we will get there, slowly, in our own time, as we continue this quiet journey together, gently moving forward. After the planetary nebula has been shed, what remains of the sun will be its core, a dense, hot, compact object called a white dwarf. A white dwarf is roughly the size of Earth, but it contains about half the mass of the original sun. So while the sun today is vast and spread out, the white dwarf will be tiny and extraordinarily dense. A teaspoon of white dwarf material would weigh about 1 ton. White dwarfs are among the densest objects in the universe that are not black holes or neutron stars. They are composed mostly of carbon and oxygen, the ash left behind from all those years of nuclear fusion. And we can take a moment to notice that the white dwarf is not nothing. It is a very real, very present object. Dense, small, cooling, but there, the quiet heart of the sun. Still present, still warm, still shining, just in a much more modest way. When the white dwarf first forms, it is extremely hot, perhaps 100,000 degrees Celsius at its surface. Much hotter than the current sun. It glows brilliantly, radiating heat into space. But because it is no longer producing energy through nuclear fusion, there is no more fuel to fuse. It has no source of new energy. It simply radiates away the heat that it already has. Slowly, over billions of years, it will cool. This process is called white dwarf cooling, and it takes an extraordinarily long time. Models suggest that it takes tens of billions of years for a white dwarf to cool significantly. And we can take a moment to notice how patient that cooling is. Not a sudden switch off, but a slow, gradual dimming, like a rock taken from a fire, sitting in the open air, releasing its warmth very slowly, quietly, over a span of time longer than the current age of the universe. Now, as we continue, white dwarfs are supported against gravity not by the pressure of nuclear reactions, but by a quantum mechanical effect called electron degeneracy pressure. In ordinary matter, electrons occupy specific energy levels, and in a white dwarf, the electrons are packed so densely that they resist being compressed further. According to a fundamental quantum rule called the Pauli exclusion principle, this quantum pressure is what holds the white dwarf up. It does not depend on temperature. It does not depend on ongoing reactions. It is simply a property of matter under extreme compression, a deep, quiet stiffness built into the fabric of quantum physics. And we can take a moment to appreciate that this quantum effect, invisible and mysterious, is the quiet guardian that keeps the white dwarf from collapsing further. Physics, silently and reliably, holding things together. White dwarfs are surprisingly common. About 97% of all stars in our galaxy will end their lives as white dwarfs. The exceptions are only the most massive stars, which end in more energetic ways, neutron stars or black holes. But for ordinary stars like the Sun, and for the vast majority of stars in the Milky Way, the white dwarf is the final destination. There are estimated to be somewhere between 10 billion and 100 billion white dwarfs in our galaxy right now. Most of them invisible to the naked eye because they are small and faint. The night sky is full of these quiet remnants, cooling slowly, dimming gradually, drifting through the galaxy in the dark. And we can take a moment to notice that the darkness between the stars is not empty. It is gently populated with these ancient, fading lights, slowly cooling, quietly present. Let's take a quiet moment to think about one of the most famous nearby white dwarfs, Sirius B. Sirius, the brightest star in the night sky, is actually a binary star system. The bright star you can see is Sirius A, but orbiting it is a faint, compact companion called Sirius B, a white dwarf about the size of Earth. With approximately the same mass as the Sun, Sirius B was the first white dwarf ever discovered. And its detection in the 19th century helped astronomers understand that stars could exist in such extreme, compact states. It is about 8.6 light-years from Earth, one of our nearest stellar neighbors. When you look at Sirius sparkling in the winter night sky, you are looking at a double system. One star still in its prime and one ancient, cooling remnant quietly orbiting beside it. Two stars, two different stages of life, together in the dark, gently moving forward. A cooling white dwarf goes through color changes as it cools. When it first forms, it is white-hot, radiating intensely. As it cools over billions of years, it becomes yellowish, then orange, then red. Eventually, after an almost unimaginable amount of time, it may cool enough that it no longer glows visibly at all. At that point, it would become what is called a black dwarf, a dark, cold, inert ball of carbon and oxygen drifting silently through space. However, and this is a very soft, quiet fact, no black dwarfs are believed to exist yet. The universe is about 13.8 billion years old. And models suggest it takes longer than that for a white dwarf to cool to the point of becoming a black dwarf. So in all the vastness of the observable universe, there are currently no black dwarfs. They are objects of the very distant future, waiting patiently to form. Long after most stars have come and gone, there is something poetic about the idea of a black dwarf, an object so old, so fully cooled, that it no longer emits any light at all. A cold, dark sphere of crystallized carbon drifting silently through an increasingly quiet universe. Some models suggest that the interior of a sufficiently cooled white dwarf would be crystallized. The carbon and oxygen atoms would arrange themselves into a crystalline lattice, essentially making the white dwarf a giant, cold crystal. In a very real sense, the final form of the Sun, in the very distant future, might be a vast crystal of carbon floating silently in space. There is something extraordinarily quiet and beautiful about that image. Not a dramatic ending, but a crystalline stillness. The Sun, slowly transformed over trillions of years, becoming a crystal in the dark, slowly, gently, resting at last. Now, as we continue, white dwarfs sometimes have companions. If a white dwarf has a nearby companion star that is still burning, it can slowly draw material from that companion through gravity. This material, mostly hydrogen, builds up on the surface of the white dwarf. Occasionally, when enough hydrogen has accumulated, it ignites in a sudden burst of nuclear fusion, causing the white dwarf to briefly brighten dramatically. This event is called a nova. It is not the complete destruction of the white dwarf. It is more like a brief flare, a momentary brightening, followed by a return to the quiet glow of the white dwarf beneath. The white dwarf survives the nova and continues to slowly accumulate more material from its companion. Over time, if enough material accumulates, this process may repeat, quietly, periodically, like a very slow, very dim heartbeat in the dark. Let's take a quiet moment to think about one specific white dwarf type, the DA white dwarf. Most white dwarfs are classified by their spectra, the light they emit, and the most common type is the Da white dwarf, which shows only hydrogen in its spectrum. This is because, despite the interior being carbon and oxygen, hydrogen is so light that it floats to the top of the star and forms a thin layer on the surface, covering the carbon and oxygen beneath. It is a bit like cream floating on the surface of a cup of coffee. The lighter material naturally settles at the top. And we can take a moment to notice that even in this quiet, late stage of stellar life, physics is still gently organizing things, still sorting matter by density and weight, still doing its quiet, patient work. The universe does not stop being orderly just because a star is old and cooling, gently moving forward. One of the most profound things to understand about white dwarfs is the relationship between their mass and size. For ordinary objects, if you add more mass, they get bigger. But for white dwarfs, the opposite is true. The more massive they are, the smaller they become. This is because the quantum pressure holding them up is overwhelmed more effectively by stronger gravity. So a heavier white dwarf is actually more compressed. There is an upper limit to how massive a white dwarf can be, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit, named for the Indian physicist Subramanian Chandrasekhar, who calculated it in the 1930s. If a white dwarf exceeds this limit, the quantum pressure can no longer support it, and it collapses, often triggering an enormous explosion called a Type Ia supernova. But for the Sun's white dwarf remnant, which will be well below the Chandrasekhar limit, there will be no such explosion. Just slow, quiet cooling. Just rest, gently moving forward. It is a soft and quiet thing to think about what the solar system will look like long after the Sun has become a white dwarf. The outer planets, Jupiter, Saturn, Uranus, Neptune, will likely still be present, though they will be very cold and dark. Without the Sun's warmth, these planets will cool to temperatures just a few degrees above absolute zero. Their atmospheres may partially freeze out onto their surfaces over very long timescales. And we can take a moment to imagine that very distant future solar system. The former Sun, now a tiny white dwarf, a dim point of light, perhaps glowing like a bright star in the sky as seen from Jupiter's frozen moons, hanging silently in space. The planets, vast and dark and cold, quietly orbiting this faint remnant. The whole system hushed, patient, slowly cooling into the deep future. Now, as we continue, the gravitational dynamics of the solar system will also change after the Sun becomes a white dwarf. As the Sun sheds its outer layers during the red giant and planetary nebula phases, it will lose a significant fraction of its total mass. The Sun will end up as a white dwarf with roughly half of its current mass. When the central body of a gravitational system loses mass, the orbits of the planets surrounding it expand. The planets will move outward as the Sun loses mass. Jupiter, which currently orbits at about 5.2 astronomical units from the Sun, might eventually orbit at perhaps 10 or more astronomical units. The whole solar system will gently expand, like a fist slowly opening into an open hand. Slowly, gently, the planets drifting outward into larger, quieter orbits around a dimmer, smaller star. Let's take a quiet moment to think about the moons of the outer planets during this long future period. Many of the moons of Jupiter and Saturn are currently frozen worlds covered in ice. During the red giant phase, when the Sun briefly becomes vastly larger and more luminous, these moons may experience a brief warming, perhaps enough to melt some of their surface ice, creating temporary oceans or lakes. Models suggest that this warming could last for hundreds of millions of years. which in biological terms is a very long time. There is a quiet, speculative possibility that during this warming period, if any of these moons have the right chemical ingredients, life could briefly flourish there, even as the inner solar system is being consumed. And then, as the sun fades to a white dwarf, those oceans would slowly freeze again. A brief, quiet summer in the outer solar system, then darkness and cold, gently moving forward. The moon, which currently orbits the Earth at about 384,000 kilometers, will experience changes too as the sun evolves. The moon's orbit is slowly growing, about 3.8 centimeters per year, as the Earth's tidal forces gradually transfer energy to the moon. Over billions of years, this gradual drift will continue. By the time the sun enters its red giant phase, the moon will be noticeably farther from Earth than it is today. What we might take a quiet moment to notice is that even the moon and Earth are in a kind of slow, ongoing dance, changing their relationship very gradually, year by year, centimeter by centimeter, over billions of years. The night sky of the very deep future will look different from tonight's sky, even just from the moon being slightly further away. But for now, the moon hangs beautifully where it is, slowly drifting, but still close, still softly lighting the night. Now, as we continue, the white dwarf sun will emit light and heat for an extremely long time, but in decreasing amounts. A newly formed white dwarf emits a great deal of ultraviolet light, which gradually shifts to visible light as the dwarf cools. Over billions of years, the emission will shift to infrared, heat radiation rather than visible light, and then eventually the white dwarf will be too cool to emit much energy at all. By then, it will have become a black dwarf, as we mentioned softly earlier, and the solar system, whatever remains of it by that point, will be orbiting in near total darkness, lit only by the faint, distant light of other stars. The former sun, now a dark crystal of carbon, will be invisible except by its gravitational pull on the remnant planets still quietly orbiting it. Slowly, gently, the last light fading, an old system finally at rest. Let's take a quiet moment to think about how the sun compares in all of this to more massive stars. Stars that are much more massive than the sun live much shorter lives. A star 10 times the mass of the sun burns through its fuel in only about 30 million years, a tiny fraction of the sun's 10 billion year lifespan. And when such a star dies, it does so far more dramatically, a supernova explosion, bright enough to briefly outshine an entire galaxy. The remnant is not a gentle white dwarf, but a neutron star or a black hole. The sun, being modest and average in mass, is spared this dramatic fate. It will end its life quietly, gently, shedding its layers softly into the cosmos, leaving behind a small, cooling white dwarf. And we can take a soft moment to appreciate the peacefulness of that ending. Not dramatic, not explosive, just a long, patient, gentle dimming, gently moving forward. There is a concept in astrophysics called nucleosynthesis, which refers to the creation of new atomic nuclei, new elements inside stars. The Big Bang produced mostly hydrogen and helium. Everything heavier than that, carbon, oxygen, nitrogen, iron, calcium, gold, was created later, inside stars, or in violent stellar explosions. The sun, during its lifetime, will create carbon and oxygen through helium fusion in its later stages. These elements, released into space when the sun sheds its outer layers, will join the interstellar medium and eventually become part of new stars and planets. And we can take a quiet moment to appreciate that the carbon in your body, the carbon in every cell, in every molecule of DNA, was created in the core of an ancient star that lived and died long before the sun was born. We are made of old starlight. We are the universe. Very gently, becoming aware of itself. Now, as we continue, the sun's magnetic field, which is currently responsible for sunspots, solar flares, and the beautiful structure of the solar corona, will change dramatically during the red giant phase. As the sun expands, its rotation will slow down, much like a spinning ice skater who spreads their arms will spin more slowly. As rotation slows, the magnetic field will weaken. The sunspot cycle that the sun currently goes through every 11 years will likely slow or change as the sun ages. In the white dwarf phase, the sun will still have a magnetic field, but it will be very different, perhaps much stronger in some white dwarfs due to the compression of the field during the collapse, and much weaker in others. Each white dwarf has its own magnetic personality, and we can take a soft moment to notice that even in old age, even in the quiet of a cooling white dwarf, the universe still has its own complex, individual character. Let's take a quiet moment to think about how we know all of this. How can scientists predict, with confidence, the future life and death of the sun, when no human has ever witnessed a star like the sun going through its end stages? The answer is that the universe is so vast and contains so many stars that it is essentially showing us all stages of stellar evolution simultaneously. Some stars in our galaxy are young, just forming. Others are in their middle life, like the sun. Others are in the red giant phase. Others are planetary nebulae. Others are already white dwarfs. By studying all of these different stars, and by understanding the physics of nuclear fusion, gravity, and thermodynamics, astronomers can piece together the complete life story of a star. The sun's future is known to us because we can see older, similar stars that have already walked that path. We are reading the story from the ending backward. Very softly, very carefully, gently moving forward. The universe has a preference for stability and balance, as we have noticed several times in this quiet journey. This preference is called thermal equilibrium, and it applies to cooling objects as well. A white dwarf cools not dramatically, not in fits and starts, but in a smooth, continuous, mathematically regular way. Its temperature at any given time can be predicted from its age with remarkable precision. Physicists have constructed detailed models of white dwarf cooling curves, and these models are so reliable that astronomers use white dwarfs as cosmic clocks by measuring the temperature of the coolest white dwarfs in a cluster of stars. They can determine how long ago those stars formed. The white dwarfs, slowly cooling in the quiet dark, are telling us the age of the stars that preceded them. Even in silence and darkness, they are still speaking, still contributing, still quietly useful. Now, as we continue softly together, let us take a moment to think about the sun in the context of the entire Milky Way galaxy. Our galaxy is a vast, slowly rotating spiral of gas, dust, and roughly 200 to 400 billion stars. The sun is located about halfway out from the center, in a quiet region of one of the spiral arms, called the Orion Arm. The sun orbits the center of the galaxy once every roughly 225 to 250 million years. This is called a cosmic year. In the 4.6 billion year life of the sun, it has completed about 20 galactic orbits. As you lie quietly tonight, the entire solar system is moving through the galaxy at roughly 220 kilometers per second, in a great, slow, circular orbit around the galactic center. And we can take a moment to notice that even in sleep, even in stillness, You are traveling at extraordinary speed through the galaxy. The cosmos is always in motion, always gently turning. Let's take a quiet moment to think about the other stars in our neighborhood. The nearest star to the Sun is Proxima Centauri, a small, dim red dwarf about 4.24 light-years away. Red dwarfs are the most common type of star in the galaxy, and they are much smaller and cooler than the Sun. They burn their fuel so slowly and efficiently that they can live for trillions of years, far longer than the current age of the universe, where the Sun has a lifespan of about 10 billion years. A red dwarf like Proxima Centauri may live for 4 or 5 trillion years. And we can take a soft moment to appreciate that the Sun, in the cosmic neighborhood, is something of a middle-aged professional, not as long-lived as the small, slow-burning red dwarfs, but not as brief and brilliant as the massive blue stars. Just a steady, average, dependable star, living its life quietly and fully, gently moving forward. There is a concept in astronomy called the stellar life cycle, which describes the complete sequence of events from the birth of a star to its final fate. All stars are born in the same way, from clouds of gas and dust called nebulae, which slowly contract under gravity over millions of years, heating up as they compress, until nuclear fusion ignites in the core and a star is born. The nebula that gave birth to the Sun was a large cloud of gas and dust in our young galaxy. About 4.6 billion years ago, something, perhaps a nearby supernova explosion from an even older star, may have compressed the cloud slightly, triggering the collapse that led to the formation of the Sun and its planets. And we can take a moment to think about that connection. The Sun may owe its very existence to the death of an even older star, whose supernova gently nudged a quiet cloud of gas into collapse and new life. Now, as we continue, the universe itself has a life story, just as stars do. The universe began about 13.8 billion years ago with the Big Bang, and has been expanding and cooling ever since. In its earliest moments, there were only hydrogen and helium. The first stars formed about 200 to 300 million years after the Big Bang. These were very massive, very hot, very short-lived stars that produced the first heavy elements through fusion and supernova explosions. The material from these first-generation stars enriched the gas clouds of the early universe, making them more complex. Over billions of years, this cycle of star formation, element creation, stellar death, and recycling has produced the rich, complex universe we live in today. A universe where ordinary stars like the Sun can form with enough carbon, oxygen, and iron to build rocky planets and living things. And we can take a soft moment to appreciate the depth of that history. How many generations of stars had to live and die before the Sun could form and life could begin? Let's take a quiet moment to think about the eventual fate of the universe itself. The universe is expanding, and current evidence suggests that this expansion is accelerating, driven by something called dark energy. In the very far future, on timescales of trillions and quadrillions of years, the universe will continue to expand. Stars will gradually stop forming as gas clouds are used up. Eventually, even the longest-lived red dwarfs will burn out, leaving a universe populated mostly by cooling white dwarfs, neutron stars, and black holes, all slowly moving apart in an increasingly dark and quiet cosmos. This era is called the degenerate era by some cosmologists, and it has a kind of quiet, melancholy beauty to it. A vast, dark, mostly empty universe, with only these quiet remnants slowly cooling and drifting apart. There is something deeply peaceful about that image. In its own way, the universe, at last, growing calm and still, gently moving forward. Let us return softly to the sun itself for a moment. The sun's light takes about 8 minutes to reach Earth, as we mentioned earlier, but it takes about 43 minutes to reach Jupiter, about 80 minutes to reach Saturn, about 2.7 hours to reach Uranus, and about 4.2 hours to reach Neptune. So the outer solar system is receiving the sun's light very significantly delayed and at greatly reduced intensity. Neptune, for example, receives about 900 times less sunlight than Earth does. This is why Neptune is so bitterly cold, despite being in the same solar system. The same sun that feels warm on your face right now. That same light takes more than 4 hours to reach Neptune and arrives there as a dim, faint brightness. The sun visible from Neptune would look like a very bright star, not the great golden disk we see. And we can take a soft moment to feel the scale of that quiet, vast, sunlit system stretching out from us in all directions. Now, as we continue, one of the more remarkable things about the sun is that it does not exist in isolation. It was formed as part of a stellar nursery, a large region of gas and dust in which many stars formed around the same time. Some of those stars may still be in the galaxy, now scattered across the Milky Way by hundreds or thousands of light years. Astronomers have recently identified what they call solar siblings, stars that may have formed from the same nebula as the Sun and are now scattered across the galaxy. One candidate solar sibling, called HD 162826, is located about 110 light-years from Earth. It is a star slightly more massive than the Sun, also about 4.6 billion years old, with a similar chemical composition. And we can take a quiet moment to notice that the Sun has siblings, stars that were once neighbors, now separated by the slow drift of galactic time, living their own quiet lives in different parts of the galaxy. Let's take a quiet moment to think about the sound of the sun. The sun is not silent. It vibrates constantly, millions of pressure waves, like sound waves, rippling through its interior. These oscillations are caused by turbulent convection in the outer layers of the sun, and they set the entire star ringing like a very complex bell. Astronomers study these oscillations using a technique called helioseismology, which is analogous to how geologists use earthquakes to study the interior of the Earth. By analyzing the frequencies of the sun's oscillations, scientists can probe deep into the sun's interior, regions we cannot see directly. The sun, in a very real sense, is constantly humming. If you could hear it, it would produce a very low, very complex chord, mostly bass frequencies far below the range of human hearing. But it is there, always vibrating, always resonating, in the quiet depths of its own immense body, gently moving forward. The sun's energy output, the total amount of energy it radiates into space each second, is called its luminosity. The sun's luminosity is about 3.8 times 10 to the power of 26 watts. That is 380 trillion watts of energy, pouring into space in all directions every second. Of all that energy, the Earth intercepts only a tiny fraction, about 1/2 billionth of the sun's total output. Even that tiny fraction, however, is enough to power all of Earth's weather, all ocean currents, all plant photosynthesis, and, through those plants, essentially all life on Earth. And we can take a moment to notice how generous the sun is. In a very quiet way, it pours this immense energy into space in all directions. And our small blue planet gently catches just a little of it, just enough, and uses it to sustain the extraordinary complexity of life. Slowly, gently, just enough. Now, as we continue, The sun's luminosity is not perfectly constant. It varies slightly over the course of the 11-year solar cycle. At solar maximum, the sun is about 0.1% more luminous than at solar minimum. This small variation has some measurable effect on Earth's climate. But scientists are careful to distinguish this natural variation from longer-term climate trends driven by other factors over the sun's entire life. However, its luminosity has increased significantly. When the sun was young, it was roughly 70% as luminous as it is today. And over the next 5 billion years, it will continue to brighten. By the time the sun enters its red giant phase, it will be several times more luminous than it is now. The sun is slowly getting brighter, even as it sits quietly in its main sequence phase. Very slowly, too slowly to notice in any human lifetime, but measurably, over millions of years. Let's take a quiet moment to think about the concept of deep time. Geologists and astronomers use this phrase to describe timescales that are far beyond ordinary human experience. A human life is perhaps 80 years. Recorded human history spans about 5,000 years. The entire time since the extinction of the dinosaurs is about 66 million years. The sun is 4.6 billion years old. The universe is 13.8 billion years old. These are the depths of time, quiet, almost incomprehensible depths. And one of the most calming things about deep time is that it dissolves urgency. In the context of deep time, even the longest human concerns are very brief. The things we worry about on ordinary evenings exist in a tiny sliver of the great, slow, patient story of the universe. And we can take a moment to let that softness settle over us, the vastness of time, gently putting our small concerns into a very peaceful perspective, gently moving forward. There is a beautiful thought experiment sometimes used by astronomers to convey deep time. Imagine compressing the entire history of the universe, 13.8 billion years, into a single calendar year. On this cosmic calendar, the Big Bang happens on January 1 ST. The Milky Way galaxy forms around March. The Sun and Solar System form around September 2 ND. The first life on Earth appears around September 21 ST. Dinosaurs appear on December 25 TH. All of recorded human history, every civilization, every war, every invention, every art, every person who has ever lived, happens in the last 10 seconds of December 31 ST. And we can take a soft, quiet moment to feel what that means. The entire span of human experience, all of it, fits in the last 10 seconds of the cosmic year. We are very new here. The universe is very old, and there is something deeply peaceful in that perspective. Now, as we continue, the atoms in your body are, in a very real sense, as old as the universe. The hydrogen atoms in your body, in the water in your cells, were formed in the first few minutes after the Big Bang, 13.8 billion years ago. The carbon, nitrogen, oxygen, calcium, and iron in your body were created in the cores of stars that lived and died before the sun was born. You are made of atoms that have been part of supernovae, of ancient nebulae, of stellar cores, of interstellar gas clouds, of comets, of rocky planets. Your atoms have been in many places, over an almost unimaginable span of time. And we can take a quiet moment to feel that deep history, the silent, patient journey of atoms that eventually found their way into you. Tonight, resting comfortably, in this present moment, let's take a quiet moment to think about the sun's place in the Hertzsprung-Russell diagram. This is one of the most important tools in astronomy, a graph that plots stars by their luminosity and their surface temperature. When you plot thousands of stars on this diagram, They arrange themselves into clear patterns. Most stars, including the Sun, fall on a diagonal band called the main sequence. More massive, hotter, brighter stars sit at the upper left. Less massive, cooler, dimmer stars sit at the lower right. The Sun sits comfortably in the middle of this band, a very ordinary, very average star. As a star evolves and ages, its position on the diagram shifts. It moves off the main sequence toward the giant branch, then shifts again as it becomes a white dwarf. The diagram is, in a sense, a quiet map of stellar life, and the Sun has been steadily occupying its calm middle position for 4.6 billion years, gently moving forward. Our Sun is sometimes described as a population 1 star. This refers to a classification of stars based on their chemical composition. Population 1 stars are relatively rich in elements heavier than hydrogen and helium, things like carbon, oxygen, iron. These are stars that formed after earlier generations of stars had already lived, died, and enriched the interstellar medium with heavy elements. Population 2 stars, by contrast, are older and poorer in heavy elements. They formed before many supernovae had occurred, so they have less carbon and iron than the Sun. Population 2 stars are found mostly in the older parts of galaxies, like globular clusters, and we can take a moment to notice that the Sun, by being rich in heavy elements, is the product of multiple previous generations of stars. It carries within it the history of the galaxy, written in atoms, in the quiet chemistry of its own composition. Now, as we continue, the concept of entropy is relevant here. Softly and gently, entropy is, in simple terms, a measure of disorder or randomness in a system. The second law of thermodynamics tells us that in any closed system, entropy tends to increase over time. The universe, over very long timescales, is moving toward greater and greater entropy, greater and greater disorder. Stars are bright, organized structures that locally reduce entropy by converting the diffuse energy of gravity into the compact energy of heat and light. But this process cannot continue forever. Eventually, over the deep future, all stars will burn out, all black holes will evaporate, and the universe will reach a state of maximum entropy, a cold, dark, uniform state sometimes called the heat death of the universe. This is the furthest possible future, trillions of years from now, and we can take a very soft moment to notice that even the universe, like all things, is moving very slowly, very gently, toward rest. Let's take a quiet moment to think about the composition of the Sun more carefully. We mentioned that the Sun is about 73% hydrogen and 25% helium by mass. But it also contains small amounts of oxygen, carbon, neon, iron, nitrogen, silicon, magnesium, sulfur, and many other elements. Even in these tiny quantities, these elements leave their fingerprints in the Sun's spectrum. Iron, for example, has thousands of spectral lines in the Sun's spectrum. By carefully measuring these lines, astronomers can determine the exact abundance of each element in the Sun's atmosphere. And the interesting thing is that the Sun's composition reflects the average composition of the universe as a whole quite closely. The Sun is, in a sense, an average sample of the universe, a quiet, representative star, made of the typical cosmic mix of elements. Just like most stars, just like most of the ordinary matter in the cosmos, gently moving forward. The word nucleus comes from the Latin word for kernel or core, and the atomic nuclei that fuse inside the Sun really are like kernels, tiny, dense centers of atoms, carrying most of the atom's mass in a very small space. An atomic nucleus is about 100,000 times smaller than the atom as a whole. If an atom were the size of a football stadium, the nucleus would be the size of a marble at the center. And yet, almost all of the atom's mass is in that marble-sized nucleus. The rest of the atom, the electrons swirling around it, is mostly empty space. And we can take a quiet moment to notice that the solidity we feel in everyday objects is mostly an illusion of electron repulsion. The matter around us, including our own bodies, is overwhelmingly empty space at the atomic level. We are, mostly, gently, made of nothing, with a little nuclei scattered through the void. Now, as we continue, let us think about a very soft and interesting fact about the sun's age relative to the universe. The universe is about 13.8 billion years old. The sun is about 4.6 billion years old. So the sun formed when the universe was already 9.2 billion years old, about 2/3 of the way through the current age of the universe. This means that there were many stars that lived complete lives and died before the sun even formed. The heavy elements in the sun and in us are the legacy of all those earlier stars. We are third generation, perhaps fourth generation cosmic matter. And we can take a soft moment to appreciate the patience of the universe. 9 billion years of stellar cycling, of stars forming and dying and enriching the cosmos, before the right conditions existed to form a sun like ours, a planet like Earth, and life like us, slowly, gently, the universe building complexity, one generation at a time. Let's take a quiet moment to think about the relationship between the sun and time itself. Time, in our everyday experience, feels constant and uniform. But according to Einstein's general theory of relativity, time is actually affected by gravity. Near a massive object, time runs slightly slower. At the surface of the sun, time runs very slightly slower than it does here on Earth, about 2 parts per million slower. This is a tiny effect, barely measurable by any direct means. But it is real. Over the 4.6 billion year life of the sun, this tiny difference in the rate of time at the sun's surface compared to far away in space has accumulated into a real, if small, difference. And we can take a soft moment to appreciate that the universe is subtle in this way, that even the flow of time is not uniform, but gently curved and shaped by the presence of mass. Even time is soft and flexible. In the long, quiet grammar of physics, gently moving forward, the energy that the sun produces has made life on Earth possible. But it does so in a surprisingly roundabout way. The sun's energy reaches Earth. As sunlight, plants capture this sunlight through photosynthesis, using it to combine carbon dioxide and water into sugar. Animals eat plants, or eat other animals that ate plants. So essentially, all food on Earth, every meal, every calorie, traces its origin back to sunlight and the warmth that keeps the Earth's surface above freezing is also solar energy, absorbed by the surface, an atmosphere. In a very deep sense, we are solar-powered beings. Our warmth, our food, our movement, all of it ultimately came from the nuclear reactions in the sun's core, traveled 150 million kilometers through space, and was captured here, on our small, gentle, blue planet. We are sunlight, quietly transformed into life, slowly, gently, over billions of years. Now, as we continue, the phenomenon of photosynthesis is one of the quieter miracles of biology. A plant takes in sunlight, water, and carbon dioxide, and through a complex series of chemical reactions, produces glucose, a simple sugar, and releases oxygen. As a byproduct, every breath of oxygen you take tonight was produced by a plant or by photosynthetic microbes. In the ocean, the oxygen in Earth's atmosphere is entirely biological in origin. It was produced by living things over billions of years. Before life began, Earth's atmosphere had almost no free oxygen, and we can take a soft, quiet moment to appreciate that breath. The slow, gentle rise and fall of your chest is itself a connection to sunlight, to ancient biology, to the long history of life on this planet. Every breath is a small chapter in the story of the sun. Slowly, gently, let's take a quiet moment to think about the sun's effect on Earth's climate over geological time. Scientists have found evidence in rock layers, ice cores, and ocean sediments for periods of significant climate change. Over Earth's history, some of these changes were driven by variations in Earth's orbit and tilt, a cycle discovered by the Serbian scientist Milutin Milankovic. Earth's orbit changes shape slightly over cycles of about 100,000 years, becoming more or less elliptical. Earth's axial tilt changes slightly over cycles of about 41,000 years, and Earth's axis wobbles slowly over about 26,000 years. These subtle orbital changes alter how much sunlight reaches different parts of Earth at different times of year, contributing to the advance and retreat of ice ages. The sun's influence on Earth's climate is not just direct, but mediated through these long, slow orbital rhythms, gentle cosmic cycles, turning on timescales far beyond any human life, gently moving forward. There is a very quiet and beautiful concept called the Goldilocks zone, which we mentioned earlier as the habitable zone. But let us sit with it a little more gently. The habitable zone is the region around a star where conditions are just right for liquid water, not too hot, not too cold, just right. Earth, by fortunate circumstance, sits right in the middle of the sun's habitable zone. This seems obvious to us because we live here and the planet seems normal, but astronomers who study other star systems find that many planets are too close to their star, baked and dry, or too far, frozen and dark. The fact that Earth sits so comfortably in this quiet, mild zone with its liquid oceans and moderate temperatures is part of what makes life here possible, and we can take a quiet moment to feel that gentleness. The Earth, not too hot, not too cold, held softly in just the right place by the sun's gentle warmth. Now, as we continue, there is a process happening in the sun called the solar cycle, which we mentioned earlier in terms of sunspots. But let us think about it a little more gently. The sun's magnetic field is constantly tangling, twisting, and reorganizing itself. This is because the sun rotates differentially, faster at the equator, slower at the poles, and this differential rotation winds up the magnetic field lines, like spaghetti, twisting around a fork. Slowly, over years, eventually, the field becomes very tangled and complex, producing the maximum of solar activity. Then the field is reorganized and even flips its polarity. North becomes south, and south becomes north, and a new quieter cycle begins. This magnetic flip happens every 11 years, so the sun's magnetic field completes a full cycle of returning to its original polarity every 22 years. A slow, silent, magnetic heartbeat, a deep rhythmic breath of the sun cycling slowly through the decades. Let's take a quiet moment to think about the solar corona. The corona is the outermost layer of the sun's atmosphere, a thin, wispy halo of plasma that extends millions of kilometers into space. Normally, the corona is invisible because it is so much fainter than the bright disk of the sun. But during a total solar eclipse, when the moon perfectly covers the sun's disk, the corona becomes visible to the naked eye as a soft, white, shimmering halo around the darkened sun. It is one of the most beautiful sights in nature, suddenly visible only because of the precise coincidence that the moon, at its current distance, appears almost exactly the same size as the sun in our sky, and we can take a soft moment to appreciate that perfect geometric coincidence. The moon, just the right size and just the right distance to briefly reveal the sun's hidden crown of light. Slowly, gently, a natural miracle of alignment, gently moving forward. The sun's corona is so hot, 1 to 3 million degrees Celsius, that scientists have debated for decades why it is so much hotter than the surface below it. The most widely accepted explanations involve the transfer of energy from the sun's convective interior to the corona through magnetic waves and magnetic reconnection events. When magnetic field lines in the corona snap and reconnect, they release energy like a rubber band snapping, and this energy heats the coronal plasma. These are called nanoflares, tiny, frequent releases of energy distributed across the corona, heating it from below. And we can take a quiet moment to notice that the sun, even in its quiet periods, is constantly undergoing these small, local releases of energy, like the surface of a quietly simmering body of water, always slightly alive, with small motions, small releases, small adjustments, never truly still, but never dramatic, just gently active. Always. Now, as we continue, one of the most peaceful things to understand about the sun is its enormous thermal mass. The sun is so massive and so hot that even if fusion were to suddenly stop, which it will not, but as a thought experiment, it would take the sun millions of years to cool noticeably. The energy stored in its vast, hot body is so immense that it would continue radiating heat into space for an extraordinary length of time, even without new energy being produced. The Kelvin-Helmholtz timescale, the time it would take the sun to radiate away all its thermal energy, is estimated at about 20 million years, and we can take a soft moment to appreciate the depth of that thermal reserve. The sun is so warm, so deeply stored with heat, that even in the impossible hypothetical of stopped fusion, it would glow warmly for 20 million years. It is not easily dimmed. It is patient in its warmth. Let's take a quiet moment to think about the relationship between the sun and the night sky that we see. All the stars visible in the night sky are other suns, other stars in our galaxy, most of them similar to our own. The closest stars are a few light years away. The farthest stars, visible with the naked eye, are perhaps a few thousand light years away. Every pinpoint of light you can see on a clear night is a burning nuclear furnace, many of them with their own planetary systems, possibly their own planets, inhabitable zones, possibly their own forms of life. Looking up at their own night sky and seeing our sun as one of those quiet, distant points of light, and we can take a soft moment to feel the companionship of that thought. Out there, among the soft stars. Other worlds are resting too. Other nights are passing. Other quiet moments are unfolding. In the dark, gently moving forward. The sun's neutrinos, which we mentioned earlier, have been the subject of one of the most fascinating puzzles in 20th century physics. For decades, physicists measured the number of neutrinos arriving from the sun and found that it was only about 1/3 of what fusion models predicted. This was called the solar neutrino problem, and it was a serious discrepancy that troubled scientists for 30 years. The solution, discovered in the 1990s and 2000s, was remarkable. Neutrinos are not one thing, but three kinds: electron neutrinos, muon neutrinos, and tau neutrinos, and they can change from one type to another as they travel. This is called neutrino oscillation, and it requires neutrinos to have a tiny but non-zero mass, which was a new discovery. The solar neutrino problem was solved not by fixing the solar models, but by discovering a new property of matter itself. The sun, quietly and patiently, forced us to learn something fundamental about the universe. Now, as we continue, very softly, let us think about what it means for the sun's energy to have traveled so far. The light reaching us from the sun left its surface 8 minutes ago, as we mentioned gently before, but the energy in that light was created in the sun's core, perhaps 170,000 years ago, before slowly working its way outward. So in a very real sense, the sunlight of this afternoon was carrying energy that was born in the Neolithic period, before agriculture, before recorded civilization. And we can take a quiet moment to sit with that. The energy in today's sunlight is ancient. It has been traveling through the body of the sun since before the first cities were built. And now it warms your planet, your air, your days. Ancient energy, gently arriving, having traveled patiently for so very long. Let's take a quiet moment to think about the sun's future effect on Earth's water. As the sun gradually brightens over the next billion years, Earth's surface temperature will slowly rise. At some point, perhaps about 1 billion years from now, the oceans may begin to evaporate more rapidly than they are replenished. Water vapor in the upper atmosphere would be broken apart by ultraviolet radiation, and hydrogen, being very light, would escape to space slowly over millions of years. Earth could lose a significant portion of its oceans by the time the sun has lived for about 8 billion years. Earth may be a drier, hotter, quieter world than it is today. These changes will be incredibly slow, barely perceptible on any human timescale, but they are, in a very soft way, underway. The Earth, like everything in the cosmos, is slowly, gently changing, always, softly, in motion, gently moving forward. There is a beautiful relationship between the sun and the tides. The sun's gravity, combined with the moon's gravity, creates the tidal forces that cause the daily rise and fall of the world's oceans. The moon's tidal influence is about 2.2 times stronger than the sun's, because although the sun is much more massive, it is much farther away, and tidal force falls off very quickly with distance. But when the sun, moon, and Earth align, which happens twice a month, at new moon and full moon, the sun and moon's tidal forces reinforce each other, producing the larger spring tides And when they are at right angles, at quarter moons, their forces partially cancel, producing the smaller, neap tides, and we can take a soft moment to feel the slow rhythm of that, the moon and sun working together and apart, pulling the oceans back and forth in a gentle, regular tide, a quiet rhythm that has continued for billions of years. Now, as we continue, the sun is visible from a region of space much larger than our solar system. If you were stationed in a spacecraft thousands of light years away, you could still see the sun as a dim point of light, just one of hundreds of billions of faint stars making up the hazy band of the Milky Way. The sun would not be particularly prominent. It would not stand out. It would be one quiet star among many, scattered through the gentle haze of the galactic disk. And we can take a moment to appreciate that perspective. The sun, which feels so enormous and central to us, is from any cosmic distance just a small, ordinary, quietly burning point in the vast and gently glowing river of our galaxy, average and modest, doing its quiet work, giving its warmth to its small family of planets, unremarked upon by the vast universe beyond. Let's take a quiet moment to think about the minerals that will remain in the solar system after the sun becomes a white dwarf. During the red giant phase, the increased radiation from the sun will vaporize the surface layers of the remaining inner planets. Any rocky, silicate surfaces will be stripped away, or the minerals will be transformed by intense heat. Deeper in the outer solar system, comets and icy bodies will be evaporated by the red giant's warmth. Much of this material will be swept away by the solar wind, which will be much stronger. During the giant phase, what remains will be a much quieter, less populated solar system. The outer gas giants, perhaps changed in composition, orbiting slowly around a small, faint white dwarf. And we can take a soft moment to imagine that quiet future solar system. Vast, dark, mostly empty, with a few old planets still quietly orbiting, the fading memory of a once warm star, gently moving forward. One of the most profound implications of the sun's life story is what it tells us about the role of ordinary stars in the universe's story. The universe began with mostly hydrogen and helium. Through stars like the sun, heavier elements are slowly created and dispersed into the cosmos. With each generation of stars, the universe becomes richer in complexity. More carbon, more oxygen, more iron, more of the elements needed for rocky planets and biology. In this sense, stars are the universe's factories, slowly and patiently converting simple matter into complex matter. And when stars die, they return their gifts to the cosmos. Our sun, in death, will add more carbon and oxygen to the Milky Way. Future civilizations, if any exist, may be made partly of atoms that were once inside our sun. And we can take a quiet, warm moment to feel the generosity of that, the sun giving, even in its death, to the unimaginable future. Now, as we continue, very softly, let's think about the sound of silence. In the universe, space is essentially a vacuum. There is no medium through which sound waves can travel. So the sun, for all its activity, for all its convection and fusion and flares, is completely silent. From space, if you could hover just outside the sun's atmosphere, in a spacecraft, you would hear nothing, no crackling, no roaring, no humming, only Silence. The sun does all of its enormous, patient work in complete silence, as far as any distant observer is concerned. And we can take a gentle moment to appreciate that the universe is fundamentally a quiet place. All that energy, all that transformation, all those stars and explosions and nebulae happening in the deepest, most profound silence. There is no sound in space, only vast, patient, beautiful silence. And that silence, in its own way, is deeply restful. Let's take a quiet moment to think about the work of the Indian-American astrophysicist, Subramanian Chandrasekhar, who we mentioned earlier, in connection with the Chandrasekhar limit. Chandrasekhar was one of the founders of the field of stellar evolution. He made fundamental contributions to understanding how stars work, how they age, and how they die. He calculated the maximum mass of a white dwarf while traveling by ship from India to England in 1930, when he was only 19 years old. His result was initially disputed and dismissed by some more senior scientists, but eventually his work was recognized as correct and fundamental. He received the Nobel Prize in Physics in 1983, more than 50 years after making his original discovery. And we can take a soft moment to appreciate the patience in that story, a young man's quiet calculation, slowly, over decades, being recognized for the truth it contained. Good work, in the end, finds its place, gently, moving forward. The sun is sometimes called a variable star, though only very mildly so. Truly variable stars. Stars that change significantly in brightness over short periods, can dim and brighten by factors of 2 or 10 or even 1,000 over days or weeks. The sun, by contrast, varies by only about 0.1% over its 11-year cycle. This quiet stability is part of what has made Earth's climate relatively stable over geological time, and it is part of what has allowed complex life to evolve and persist. Here, a more variable star would create more chaotic conditions on any planet orbiting it. The sun's steadiness, its quiet, patient consistency, is, in a real way, a prerequisite for us being here, and we can take a soft moment to appreciate that steadiness. The sun, day after day, year after year, shining with gentle reliability, making the world as we know it possible. Now, as we continue, let us hold the 100th quiet fact. Together, we are halfway through our counting, and we can take a moment to notice how calm the story of the sun really is. It is not a story of sudden drama or violent change, but of vast, slow, patient transformation. A cloud of gas, billions of years ago, slowly condensing. Under gravity, a star igniting, quietly, and burning for 10 billion years. An expansion, over millions of years, into a red giant, a gentle shedding of outer layers, painting the space around it in soft colors. A cooling, over billions of years, into a quiet white dwarf. And then, the very longest chapter of all, a slow, peaceful cooling, over trillions of years, into the final, dark crystal. It is a long, slow, gentle story, and we are right in the middle of its most active chapter, the comfortable, warm, main sequence phase, where we live and sleep and breathe and exist. We are very lucky to be here, right now, in this part of the story. Let's take a quiet moment to think about the role of gravity in stellar formation. Gravity is the weakest, of the four fundamental forces, far weaker than electromagnetism or the nuclear forces. And yet, on astronomical scales, gravity dominates. It is the force that assembles diffuse clouds of gas into dense, hot stellar cores. It is the force that holds the solar system together. It is the force that compresses a dying star's core into a white dwarf. Gravity works slowly, over enormous timescales, but it is patient and inexorable. It does not rush. It does not stop. It simply pulls, quietly and consistently, for as long as matter exists. And we can take a moment to think about how much of the universe is shaped by this one quiet, patient force, gently gathering matter together, slowly building structures from the formless void. Slowly, gently, the quiet architect of stars and worlds, gently moving forward. The sun's surface, the photosphere, is not perfectly smooth or featureless. Even during solar minimum, when sunspots are rare, it is covered with a constantly shifting pattern of granules, those convection cells we mentioned earlier, each about the size of Texas, constantly rising and falling, rising and falling. Photographs of the sun's surface in high resolution show a texture that looks almost like a softly dimpled skin, or like the surface of a very large, very bright orange. This granulation is always present, always shifting, a quiet and constant texture of rising and cooling plasma. Each granule lasts for only about 10 minutes before breaking up and being replaced by new ones, so the surface of the sun is always refreshing itself, constantly, gently, every 10 minutes, renewing the pattern across its entire, vast surface, always in motion, always changing, always the same. Now, as we continue, there is a concept in physics called the Stefan-Boltzmann law, which describes how much energy an object radiates based on its temperature. The law says that the energy radiated increases with the fourth power of temperature. This means that if you double the temperature of an object, it radiates 16 times as much energy. For stars, this law is enormously important. It means that a star that is only slightly hotter than the sun radiates significantly more energy, and it explains why the red giant phase of the sun, despite the sun's surface being cooler and redder than today, is still much more luminous, because the enormously increased surface area more than compensates for the lower surface temperature. And we can take a soft moment to notice how elegantly these physical laws, silent, mathematical, and constant, govern the lives of stars across the universe, giving them their character, their luminosity, their color, quietly, beneath all the visible fire. The math holds everything in place. Let's take a quiet moment to think about one of the more poetic aspects of stellar death, when a star like the sun sheds its outer layers in a planetary nebula. The carbon and oxygen in those layers are, in a technical sense, being recycled, but more than that, they are being redistributed. The atoms go from being locked inside a star, unavailable for chemistry, to being free in the interstellar medium, where they can participate in the formation of new molecules, new dust grains, new asteroids, new planets. The death of a star is literally the liberation of atoms. Complex chemistry, including the chemistry of life, requires these freed atoms, and we can take a soft, warm moment to appreciate that in the very long story of the cosmos, the deaths of stars are not sad events. They are moments of release and renewal, atoms finally free to go on and become part of something new, slowly, gently, always becoming, gently, moving forward. We can take a moment to think about the speed of light. In context, light travels at about 300,000 kilometers per second. The sun is about 150 million kilometers away, so light takes about 500 seconds, 8 minutes, and 20 seconds to cover that distance. Light can circle the Earth about 7.5 times in 1 second. So in those 8 minutes of travel from the sun to Earth, light completes a journey that would take it 7.5 laps around the Earth every second for 500 seconds. It is an extraordinary journey, completed in what is, for us, a very brief time. And yet, for light itself, if we can imagine such a thing, no time passes at all. According to special relativity, a photon of light experiences zero time between its emission and absorption. The journey that takes 8 minutes, in our experience, takes zero time for the light itself. Slowly, for us, instantaneous, for light. Now, as we continue, the sun, as we have established, is about halfway through its total lifespan. This means that the sun today is roughly at the midpoint of its story, the equivalent of a human in their mid-40s or early 50s, perhaps still vital, still active, still doing its full work, but aware, in some sense, of having passed the beginning and moving into the second half, and what the second half will bring, as we have described, is a long, gradual change, a slow brightening, a gentle expansion, a beautiful shedding of outer layers, a quiet dimming into a white dwarf, and then a very, very long, silent cooling. The second half of the sun's life is longer, in some ways, and shorter, in others, than the first half, and it is, in its own way, rich and full of transformation, full of the giving back of what was gathered, slowly, gently, always full. Let's take a quiet moment to think about the sun's relationship with the Earth's magnetic field. The Earth has its own magnetic field, generated deep in its iron core by a process called the geodynamo. The motion of molten iron in the outer core creates electrical currents, which in turn create a magnetic field. This field extends far out into space, forming the magnetosphere, which deflects the solar wind and protects the atmosphere. Without the Earth's magnetic field, the solar wind would slowly strip away the atmosphere over geological time, as has happened to Mars, which lost most of its magnetic field long ago and subsequently lost much of its atmosphere. Earth's magnetic field is our quiet shield, invisible, intangible, but enormously important, a field maintained by the slow swirling of iron, thousands of kilometers below our feet, protecting our soft blue skies from the constant, quiet pressure of the sun's breath. Slowly, gently, always protecting, gently, moving forward. There is a concept in stellar physics called the mass-luminosity relation, which describes how a star's brightness relates to its mass. More massive stars are not just slightly brighter, they are dramatically brighter. A star twice the mass of the sun is about 10 times more luminous. A star 10 times the mass of the sun is about 10,000 times more luminous. This is because more massive stars have higher core temperatures and higher pressures, causing them to fuse hydrogen much faster. This is also why massive stars live so much shorter lives. They burn through their fuel rapidly, like a large bonfire that burns faster and brighter than a small candle. The sun, at its modest mass, burns slowly and lives long, and we can take a soft moment to appreciate that quiet lesson. The brightest, most dramatic, are not always the longest lived. Steadiness and patience often outlast brilliance. Now, as we continue, let us think about the color temperature of the sun's light and how it affects our experience of the world. The sun produces a spectrum of light across all wavelengths, from infrared to ultraviolet, but it peaks in the visible range around the wavelength of yellow-green light. And not coincidentally, human eyes are most sensitive to this same wavelength range. The peak sensitivity of the human eye nearly matches the peak output of the sun. This is not a coincidence. We evolved under the sun, and our visual system adapted over millions of years to make best use of the light most abundantly available. In a very literal sense, our eyes are tuned to the sun. We see the world in the sun's colors because those are the colors the sun gave us to see with, and we can take a soft moment to appreciate that deep, quiet biological connection between our bodies and this star. Let's take a quiet moment to think about what happens to the heat produced in the sun's core before it ever becomes light. The energy from fusion starts as gamma rays, high-energy photons. As they travel outward through the radiative zone, they are constantly absorbed and re-emitted by the dense solar plasma. Each absorption and re-emission randomly redirects the photon, and it performs what physicists call a random walk, a series of random steps with no preferred direction. This random walk through the sun's dense interior is why it takes so long for energy to travel from the core to the surface. At each interaction, the photon also loses a little energy, slowly degrading from gamma ray to X-ray to ultraviolet to visible light. By the time the energy emerges at the surface, it has been downshifted through many interactions, transformed from fierce gamma radiation into the gentle, visible light that makes a golden afternoon, slowly, gently transformed by the journey, gently moving forward. It is interesting to think about what the sun looks like from the surface of other planets in our solar system. For Mercury, the closest planet, the sun would appear about 3 times larger in the sky than it does from Earth, and it would move very slowly across the sky due to Mercury's slow rotation. From Mars, the sun is about 60% the angular size. It appears from Earth noticeably smaller, dimmer, and the sky would be a pale, pinkish color from fine dust. From Jupiter, the sun is tiny, like a very bright star, barely a disk, and from Neptune, the sun is just a point of light, brighter than any other star, but a small and distant thing. The same sun, seen from different distances, wearing different faces, sometimes enormous and golden, sometimes merely a bright point in a dark sky, and we can take a soft moment to feel the richness of that. One sun, so many different skies. Now, as we continue, very gently, let us think about the concept of solar wind pressure. The sun's solar wind, though made of very low-density particles, exerts a gentle pressure on everything it encounters. This pressure was first demonstrated practically in the late 20th century by the concept of solar sails, spacecraft that use large, thin reflective sheets to be gently pushed through the solar system by the pressure of sunlight, the way a sailing ship is pushed by wind. The pressure of sunlight at Earth's distance is only about 9 micronewtons per square meter, very small, but in the vacuum of space, with no friction to overcome, and given enough time, even this tiny pressure can accelerate a spacecraft to significant velocities. Several solar sail spacecraft have been tested, and the concept works. The sun, gently, quietly, without any engines or fuel, can push a sail across the solar system. A quiet, patient wind of light. Let's take a quiet moment to think about the extraordinary longevity of atoms. The carbon atom in your body has been carbon for about 13 billion years. Since before the sun was born, it has been part of many different things. In that time, a star's core, a supernova remnant, an interstellar gas cloud, a solar nebula, a rocky asteroid, perhaps another planet, and eventually Earth, and eventually the food you ate, and eventually you. And when you eventually return your atoms to the world, as all living things do, those atoms will go on to be parts of many other things for billions more years. The atoms in the sun's future white dwarf will similarly persist, crystallized and stable for trillions of years. Matter is extraordinary in its persistence. In the grand story of the cosmos, matter does not disappear. It only transforms, slowly, gently, always becoming something new, gently moving forward. When we look at the night sky, we are seeing the past. Every star you observe is seen as it was some time ago, light years ago. In fact, the star nearest to us, Proxima Centauri, appears as it was for 0.24 years ago. Sirius appears as it was 8.6 years ago. The stars of the Pleiades cluster appear as they were about 440 years ago. The Andromeda Galaxy, visible to the naked eye as a soft smudge in the sky, appears as it was 2.5 million years ago. When you look at Andromeda tonight, you are seeing a galaxy of hundreds of billions of stars as they existed 2.5 million years ago, before our species had evolved. The night sky is a time machine displaying the past at many different distances, and we can take a very soft, dreamy moment to appreciate that the whole history of the universe simultaneously visible in the dark sky above, slowly, gently, all at once. Now, as we continue, very gently, toward the end of our journey tonight, let us take a moment to think about what the sun means in terms of energy for civilization. Human civilization uses enormous amounts of energy for electricity, for heating, for transportation, for all the activities of modern life. All of the energy used by human civilization in a year is roughly equivalent to the amount of energy the sun produces in about 1 second. Just 1 second of the sun's total output would power all of human civilization for a year. And in 1 hour, the sun sends more energy to Earth's surface than all of humanity uses in a year. This is why solar energy is such a promising path for civilization. not because technology is magic, but because the energy is simply there, generous and patient, pouring down every day, waiting to be used. The sun is not stingy. It shines equally on everyone, everywhere, every day, slowly, gently, abundantly. Let's take a quiet moment to think about the fate of the sun's name. In human languages, the word sun, in English, comes from the Old English sun, which derives from Proto-Germanic roots. In many languages, the word for sun is related to the name of a deity. In Latin it is sol, giving us words like solar. In ancient Egyptian, the sun was associated with Ra. In ancient Mesopotamia, with Shamash. In Hindu traditions, Surya. In Japanese, Teo. Every human culture that has ever existed has had a name for the sun and a relationship with it, because the sun is fundamental to life. It has been humanity's most constant companion across all of recorded history and all of unrecorded history before that. And we can take a soft, warm moment to appreciate that continuity, all the different human names, all the different reverent glances upward, all pointing toward the same quiet, patient, golden star, gently moving forward. We mentioned earlier that the sun contains trace amounts of iron. Iron is one of the most tightly bound atomic nuclei. It is the element at the bottom of the fusion energy valley, meaning that fusing iron does not release energy. It requires it in massive stars that are near the end of their lives. When the core has been converted to iron, fusion stops, and the star collapses catastrophically. But the sun will never reach this stage. The sun's core will only ever fuse hydrogen and helium. The iron in the sun is simply there as a trace element, inherited from older stars. It is not produced by the sun, and it does not affect the sun's fusion. It is just present, quietly, deep inside, a relic of the previous stellar generations that donated their matter to the nebula from which the sun formed, a quiet inheritance from old stars carried along for billions of years, slowly, gently, inherited and held. Now, as we near the very end of our quiet journey together tonight, let's take a moment to think about the full arc, a cloud of hydrogen and helium, billions of years ago, slowly contracting. Under gravity, over millions of years, a protostar forming, gathering heat, until the core reaches fusion temperatures. A star igniting, the sun being born, in a nebula, long since dispersed, 4.5 billion years, of quiet hydrogen fusion, warming a small blue planet, making life possible, feeding photosynthesis, driving weather, lighting every human day that has ever happened. Then slowly, over millions of years, expansion into a red giant, the inner solar system changing, warming the outer moons, then the planetary nebula, outer layers drifting away, in a soft cloud of color, then the white dwarf, small, dense, slowly cooling. Then, after trillions of years, a cold black crystal, drifting in the dark, slowly, gently, from cloud to cloud, by way of light. Let's take a quiet moment to think about what the sun has given in its 4.5 billion years of shining. The sun has provided the energy for all life on Earth, every tree that has ever grown, every ocean that has ever been warmed, every rain cloud that has ever formed, every prehistoric creature that ever moved through prehistoric forests, every human morning that has ever dawned, every crop that has ever been harvested, every sunset that has ever colored the sky in gold and pink and orange, over the quiet turning world. All of it every bit of warmth, every bit of growth, every bit of living energy on this planet came from that one steady, patient, nuclear fire burning at the center of our solar system. And we can take a very soft, very grateful moment to acknowledge the quiet generosity of the sun. It asks for nothing. It simply shines, steadily, patiently, beautifully, giving its light to anything that happens to be nearby. And finally, the last quiet fact of our long, soft journey tonight: the sun will die, and that is true. In 5 billion years, it will begin its final transformation. But what the sun leaves behind, the elements in its shed outer layers, the planetary nebula expanding gently through the galaxy, the white dwarf cooling slowly in the quiet dark, all of that will persist. The atoms that were in the sun will go on to be part of new things, new stars, perhaps new planets. Perhaps the story does not end. It transforms. Every ending in the universe is also a beginning. The death of the sun is the birth of a planetary nebula, the creation of a white dwarf, the dispersal of carbon and oxygen into the cosmos for future stars and worlds to use in the deepest possible sense. Nothing in the universe is lost. Matter transforms. Energy disperses, patterns change, but everything continues in its new form, slowly, gently, patiently, in the long, quiet story that the universe tells itself across billions and billions of years. And we can take a moment to notice how quiet everything is right now. And so, we have come, softly and slowly, to the end of our journey tonight. We traveled from the warm, quiet present life of the sun, through its long, patient middle age, gently forward, into the distant future of its red giant expansion, through the soft colors of its planetary nebula, and finally, to the quiet, cooling peace of the white dwarf, drifting slowly through the dark. All of that, slowly, gently, over billions and billions of years, and through all of it, the same fundamental truth. The universe is not hurried. It is not anxious. It moves with extraordinary patience at its own deep, quiet pace. Stars live for billions of years. White dwarfs cool for trillions. The universe itself will persist for timescales we can barely imagine. There is no need to rush. There never was. You are here, right now, in this very comfortable moment, in the life of a medium-sized star, in an ordinary part of a typical galaxy. The sun is shining on the other side of the world. As you rest, the planets are quietly in their orbits. The neutrinos are passing through you. Gently, the universe is going about its patient, unhurried business all around you, and you can simply rest. Let the breath slow a little more, and a little more. There is no need to rush. Slowly, gently, let the thoughts soften and drift like a planetary nebula, quietly expanding in the dark, slowly becoming too diffuse to see, gently dissolving into the quiet of sleep. The sun will be there tomorrow. It will be there for 5 billion more years. There is truly nothing to worry about tonight. Just rest, just breathe, just be quietly in the enormous, patient, gentle universe. Good night. If you found this video peaceful, a gentle like and subscribe would mean a great deal. It helps more people find their way here, to this quiet place, for a restful night. Sleep well.